Good morning, everyone. So today I'm very excited to talk to you about the paper, A Control-Theoretic Approach for Dynamic Adaptive Video Streaming over HTTP. Before delving into the motivation of the paper, I'd like to talk about my motivation for presenting this paper. So this paper is, I'm not doing research in video streaming yet, and it's a decade-old paper. And in machine learning, this is like a century, right? So why I'm still presenting this paper? I think, so firstly, video streaming is still a big thing, right? And it's taking up more and more internet traffic. And what's interesting for me was that this has been the baseline for many recent works, and many of which are machine learning-based methods. And this work has shown to be very competitive to those baselines, and sometimes even better. And I was so excited, I still could remember that when I first saw some methods using machine learning for any kind of system-related problems. And because I thought I found the best hammer in the world, and everything looked to me like a nail. But of course, as I read more papers and got older, I realized that it's not a silver bullet, right? And I became increasingly appreciative of the works that tackle those fundamental problems from first principles. And I think this is one of the papers. And I think that whet your appetite a bit as well. So what is video streaming over HTTP, or what's video streaming? Who can tell me maybe in one sentence or two what video streaming is? Yeah, please.
So I guess it's like watching like a video that's not stored on your own computer.
That's completely correct. Yeah. Yeah. So it's basically allowing us to watch videos without needing to first download them, or like relying on expensive subscriptions or cable subscription or satellite. So we can watch those videos wherever or whenever we want. And really, I can't really help me like showing off this video. So this picture, this is the kind of TBS or like cable boxes I used when I was a kid to watch TV and movies. You see there's a card. This contains all the subscription you need to pay to get the thing. It was very annoying because my mom always took it away, so I couldn't watch it online. On my own. So to put things into perspective, video streaming is a really complicated service, and I like to see to get ourselves on the same page as to what kind of system components we are looking at. So we have various video sources like cameras and drones and whatnot, and they typically have an encoder surrounding them, basically responsible for transforming those raw videos into a format that can be further processed. And this will be transmitted to the nearest point of presence of the streaming platform using some transport protocol like RTM, real-time message processing protocol. And this happens automatically under the hood. And the data will be sent next to the transcoding service, which basically transcodes the video into multiple different resolutions, different versions. And these versions will be segmented or truncated into different chunks, and we typically have a whole bunch of them for each of the versions. And then we send these to a packaging service, or it packages, so to speak, the videos into different formats. For example, if you have a MacBook, we have HLS, or more generally, the Dash players. And then this will be sent to the distribution, right? So we have finished the production, video production. Now we enter the content distribution world. And basically, this is done at a content distribution network, and this will be queried or requested from the users. And what I like to highlight here is that everything happened within the streaming platform is within the managed network. Why? Because we need the performance, right? You could have what we are focusing on today, the on-demand video services, or live streaming, which is very latency sensitive. We have screen-to-screen delay within 20 or tens of seconds. But the actual distribution is over the worldwide internet. And this last mile is what we are going to focusing on. And you might know where I'm getting at, right? So for me, at least, I always set my least bar for like YouTube, for example. I always wanted to watch Full HD because I really can't stand anything murky on my screen. But what's wrong with that? I think there's nothing wrong with that, but I think it's because of the public internet, because it doesn't provide anything, right? Well, it doesn't provide any guarantees, like performance, and it's shared by many users. So on the left figure we have, on the x-axis we have the time, on the y-axis we have the video playback rate. As we can see, once a new flow joins, the rate immediately drops. And so if I always wanted to have my Full HD videos, what would happen is that I need to wait. So my kind of satisfaction goes down and I'm not happy. So this is where adaptive video bitrate streaming comes to the rescue. So now we are having our the video control panel that we're having. By the way, please stop me whenever you have questions or comments, okay? And so this is a video playing 101. So where we have is the red part, the played, the reddish part, the buffered part, and the gray part, which is the unbuffered part, okay? And as mentioned, the video is truncated into different chunks, normally tens of seconds, right? 4 seconds, 10 seconds. And then what ABR does is that it provides us with a range of options. These are just different threshold or transcoded versions we can choose from to play. And ABR will choose real time which resolution we should use for each chunk. And typically, for me, I've experienced a lot of cases, especially when I was in Zurich, where I was living in an old house and the internet was not good. So we have a kind of a slow start, right? And this is where the platform is testing how much the bandwidth you are having. So it starts from slow and later realize, well, this guy is having a good connection and raise the bar. And later we can be aggressive because we don't have anything to play later. So we can just drain the buffer using the full HD that I wanted. And of course, you can achieve this by by clicking on the cogwheel and say, I want Full HD. But of course, this is not scalable, right? And also, a word of warning, so if you change, for example, from 360p to 720p, then this will effectively clear all the buffer data. So if you tune back to the previous timestamps, then you will realize that it started downloading again because the buffer has been cleared. So the alternative solution to tuning it manually is that we can rely on ABR systems. So for ABR, what ABR does is that first it's given the buffer occupancy, basically how much video we have in our buffer in seconds, and they estimate the current throughput, and it predicts what kind of video quality we need for the next time step. And it requests the data from the video server, and the video server will respond with a manifest file, which is basically saying where the chunks are and from which URL you can get those chunks. And then we can play those video chunks on the player. So the goal of ABR is really to match, say, the throughput curve with the bitrate curve so that we can have the best possible QoE.
The buffer is in seconds, right?
Sorry?
The buffer?
Yeah.
Is in seconds.
Yeah, the buffer is in seconds. Yeah, yeah. So how much video we have in terms of seconds? So the challenge here is that firstly we need, because ABR is on the on the critical path, we want it to have low runtime and doesn't consume all of the buffer like memory on our phones, and also the environment is highly dynamic, right? So we really can't sometimes predict what will happen in the next time step. And the third challenge here is about QoE. So QoE is an overall metric, but is an all-encompassing. So in this case, we have 4 goals. We want fewer rebuffering events. We want the highest possible viewing quality and less and reduce the startup delay, for example, and less switching. I want a smoother experience, but I don't want to wait for 5 minutes to work off a 3-minute video. But the first two goal, for example, is conflicting with each other, right? So I want the way to achieve this, the fewer rebuffering events is to have always play the lowest rate. But this is conflicting with the second objective, and the same does the third objective, right? Less switching meaning that we could be less adaptive when the network condition changes over time. So this paper really focuses on improving ABR from first principles. And the first thing the author did was to model the video or the video buffering or streaming this service mathematically. So here we have x-axis the time, on y-axis the buffer, occupancy also in seconds. And the time at which we need to buffer the next video chunk, tk plus 1, can be modeled by tk plus the downloading time of the current chunk, which is the size of the current chunk divided by the throughput, plus some delta t, okay, which is the wait time. For this case, in this paper, they assume the tk is 0, meaning that we start downloading the next chunk immediately after the previous. There is an exception where the buffer is full. We need to wait, of course. And the throughput dynamic can be aggregated over the duration of the video downloading period as an average value, and the buffer dynamic is basically the difference between the downloading time and the consumption time of the current chunk, plus once we've gotten our video back, this length L, the size of video is added to our buffer. So this value is only negative when we have more time, when we spend more time on downloading than consuming the current chunk. Yeah, like I was super annoyed they used integral everywhere where they should have used summation. And now having this formulation enables us to formulate the QoE mathematically, right? So first we have the video quality, basically modeled by the sum of all the video qualities, resolution values, and we want this value to be as high as possible. And the second term is basically the video quality variation, the difference between the resolution of the current chunk and that of the previous chunk. And we want the variation to be as low as possible. And the total rebuffer time is basically, as mentioned, the difference between the buffering downloading time and the watching time and the startup delay. And we also want this value to be as low as possible. And for these terms, we can also have weights on every term and as a weighted average, as the name implies. So in the code implementation, they actually used so lambda to be 1 and mu s to be 3,000. And what this translates to is that so 1 second of rebuffering time or startup delay is equivalent of varying the buffer by 3 megabps. And from this formulation, we can have our problem being formulated as a constraint maximization on the QoE. Right? We have the time dynamics, the throughput dynamics we've mentioned, the buffer, how buffer works, as well as some system constraints as to what the set of video resolutions we can choose from are, and the buffers, the size of the buffer. And I'd like to point it out that this is a non-convex problem because we have the negative terms, which means that we need to solve this problem iteratively. Yeah, like I don't know why they put the throughput dynamics here. It's independent of the decision variables are, but I feel like I'm being a pedantic jerk. So what the problem space the authors are having in mind at that time was that, so what we want to do is that have a mapping from the current status, the state space, to the next chunk. So previously, this problem space is basically two-dimensional, where the first kind of methods uses rate-based methods where we only leverage the rate, the current downloading speed or the throughput. Or the second kind is buffer-based, where we are monitoring the buffers that we have, like what buffers look like currently. What the authors argue is that there might be another dimension that we can investigate, which is what they're proposing from a control-theoretic perspective, and specifically model predictive control is a natural fit for this problem. Well, they are not declaring this is necessarily the best or the optimal solution. Okay. If there are no questions, moving on to model predictive control, what it is. So what MPC in a very high-level overview is that we are observing the past data, and then given the past data, we are predicting what's going to happen in the future, given a fixed prediction horizon. And then we solve for the maximum or solve for the optimal choice configuration given the predictions, right? We assume that this was the future. And then we take only the first decision variable that we've made and discard the rest, and we move the prediction horizon forward and repeat. And this is basically kind of a forward-looking online learning algorithm, if you like. And I still remember when we were discussing PCC Vivace, Carter asked a question why we actually really wanted to learn this kind of thing, especially in this highly dynamic environment. I think by learning is such an overloaded term, especially in the age of machine learning and AI. I think this kind of control algorithms can also be regarded as learning, and especially in this dynamic environments, we can't really dictate our methods using fixed rules as to what they should behave in what kind of scenarios. And one interesting fact is SpaceX also used similar control methods to land their starships. Of course, it's much more complicated, and they are solving a non-convex optimization problem every tenth of milliseconds. Okay, if you're interested, feel free to look into that thing. So in the context of ABR, the exact MPC is formulated as follows. First, the authors have assumption, right? Not surprisingly, the network conditions are reasonably stable over a short time scale period. And in this case, over the next video chunks, a few seconds, should be stable. Right? So the algorithm looks like this. First, we predict the throughput using the harmonic mean over the past 5 throughput values. And we solve for the optimal configuration of the throughput, the next choice that we want to have our video resolution using the prediction. And we select the first bit prediction, bit rate prediction, and we advance the prediction window repeat. Does anyone see any problems on this slide? At least, yeah, Carter?
I mean, it seems like there's a circular dependency.
There's a circular dependency. What do you mean? Circular. Which one? Which ones?
Oh, well, I don't know. Maybe I'm thinking of something else. I mean, the big thing is the assumption. It's like quite an assumption.
Yes, I like the interactive session. Yes, I like when I was reading the paper, I was also, kind of skeptical about this assumption because this really depends on what kind of networks we are talking about, right? In wireless, for example, this changes very drastically. And also, they are using harmonic mean, which has been proven to be not so descriptive for the past data we are having. And also, they are predicting only the future throughput given the current throughput values, without taking into account other factors like the trunk size, for example. Like the downloading speed really depends on the trunk size.
Hey, could you explain a bit more about the harmonic mean? What exactly is the problem with that, or how does it work?
Yeah, so they're basically using the kind of statistics. So the question is, what's HM here, how they are using harmonic mean to predict the values. So basically, they are taking the harmonic mean. So this is not their approach. So they took the approach from a prior work. So basically saying that the harmonic mean is a useful signal to predict future this kind of time series signals as a summary, as a signal summary. And you can choose like geographic mean or arithmetic mean. For me, I couldn't wrap my head around why the harmonic mean is really useful. The only thing I used here was like for calculating F1, right? When accuracy and recall, either of them is low, then the harmonic mean is low. So it's really hard to say why this is useful, I would say. I think the authors also acknowledged that this might be a strong assumption by developing a robust MPC. So a robust version of MPC. So basically, instead of optimizing at a fixed point the prediction, which is the C hat, we are optimizing for a range of options, basically a lower bounded by bond and upper bounded by C bar. And in the paper, they've shown that this is equivalent to maximizing for the lower bound. And there's a hand-wavy proof in the paper. And the implementation, in the implementation, they basically took the maximum error over the past predictions as the lower bound to bound the value, and it turned out to work well. But there's still a problem in this solution space. Right? What is it? Think about it like this paper is a decade old, and what problems could they have at that time? Sorry, this shouldn't be a trick problem, but like we have very limited resources on our phones, right? So at that time, they said like solving this problem at every time step is quite expensive. I don't think it is still the case, because like every video chunk is about 4 seconds or 10 seconds. Solving an optimization problem at that granularity nowadays is no longer a big problem.
Do you know this?
Sorry?
Do you know this?
No what?
I mean, I don't think that like the CPUs can improve that much within 10 years. Why would this be?
TCP. Yeah, TCP wouldn't. No, I totally agree. TCP wouldn't improve that much.
No, it's not a must. Like you're saying that this optimization would be faster today.
Yeah.
Why? What is the resource that has become so faster that it would be easier?
Yeah. So what enables us to still like having faster and faster compute, or having
last
faster?
10 years we haven't done that much, like realistically.
Yeah, that is true. So I think the answer would be twofold. We have firstly the improvement on the solver side, especially on in the past decade, the solver has improved dramatically in terms of their solving skills, and we can solve problems much faster, and there are unexpected discoveries as to like the kind of NP-hard problems that we couldn't solve. Now we can have very good approximate solutions. And the second perspective is, yeah, the computer are not advancing as fast as they did previously because they're dying Moore's law. But actually, if you ask the industry people, Moore's law is still going, right? It's dying, but it's still going. By having massive parallel compute and whatnot, now we are having 3 nanometers chips. It's going much slowly, but it's still going, at least for now. Yeah, please.
So is this deployed on the client side or like on the server to solve this optimization problem?
Yeah. So the question is whether this solution is a client side or a server side solution. Yeah, that's a really, really good point. I should have pointed out that this is a client side only solution. So they argue that this would facilitate the deployment of the solutions. So we are not. So you can have, for example, server side optimizations as well. Yeah. Carter, you had a question?
I just wanted to say something I thought that was interesting from the paper.
Yeah, please.
Because you're solving a non-convex problem,
Yeah.
you use a solver like Gurobi or something. But if you were to put that client side, this is kind of a prohibitive thing because these solvers you need licenses for. So that's something they also mentioned. It's
Oh.
not just necessarily compute.
I see.
It's licensing because they're not creating the way to solve these non-convex problems. They're creating a problem that and kind of assuming it can be solved with the solver, I think.
Yeah, that's a good point. So the solvers, so the comments about like the licensing of the solver. For example, Gurobi is a commercial solver, convex optimization. No, sorry, combinatorial optimization solver. I think so. That is true. So firstly, for smaller, for example, academic licenses for a Gurobi, you can solve up to like 2,000 variables. That's a lot. And if I were the platform, I could buy the license and for my specific software that I wanted to deploy. But that could be expensive. So yeah, that's a good point. So moving on, we have, so that's why the authors developed another version, the third version, the fast MPC. So the key idea here is really to leverage something we've learned in CS undergrad, which is basically we are all in the offline state. We are enumerating the space, right? We have different buffer levels and different state spaces, and then we feed those state space offline into a solver. So in this case, this solver is from IBM. And then we do online table lookup. So this is basically dynamic programming. So we don't need to solve the problems online anyway. So we can have a kind of a cheat sheet. But you can imagine that the state space could explode. Can we have hundreds like different buffer levels and thousands of possible throughput values, for example? That could be like 10 to the power of 10 state space, right? Pretty large. So they also has something called coarsening or binning. So you just binning several rows together to coarsen the granularity of the decisions a bit. Of course, there's a natural trade-off as to like how large the bin is and the performance of the algorithm. And they also did some like a lossless compression where they combined multiple entries of the same value. So moving on to the evaluation, we have 3 workloads. First, we have a broadband dataset, a mobile dataset, and a synthetic dataset. So here are some characteristics of those datasets. On the x-axis, we have the prediction error on the throughput, and this is basically the CDF on the y-axis. And then we can see the wireless, because of the wireless environments, is so dynamic. That the prediction error is pretty high. We have a very long tail here, a very heavy tail here. It's similar where we have the mean throughput being the largest, of the mobile data set, and we have the standard deviation of how much variation there is in the data set. And also, the mobile data set stands out. So this is the hardest part, hardest data set, and we should keep an eye on this one. So the baseline methods are several, and first is the rate-based methods that takes into account only the rate, the downloading rate. The buffer-based method we've talked about. The Dash.js is basically the original ABR implementation of the Dash player at that time, and the Festive, which is also at that time a prior work of a rate-based ABR algorithm. So to compare the QoE overall, firstly, the authors compared on the FCC dataset. On the x-axis, we have the normalized QoE, and the y-axis, the CDF. Similarly, we have the synthetic dataset, as we can see. So this thick light blue line is the robust MPC. The blue line here, dark blue line, is fast MPC, and they are performing pretty well. They are on the rightest side of the figure. But if we look at and also like the buffer-based approach follows very closely to their performance. But if we look at the mobile data set on the QoE CDF, we can see that the buffer-based, they are basically in the same ballpark, right? Except for Dash.js is a bit off the chart. And the buffer-based approach and our fast MPC is pretty similar, close to each other, and the robust MPC is a bit better because of its its robust nature, I guess. So next, the authors looked at the breakdown of the QoE, right? You remember QoE is a composed matrix. So first, they looked at the average bit rate. So the higher the bit rate, the higher the quality of the videos. And on that, this is the CDF. And as we can see, and on the right, we have on the CDF for the average chain switching period, how much switching there is, how much variation there is. And as we can see, firstly, the robust MPC-based method has high bit rate, meaning that they produce high video quality and relatively low variation. This switch has not as aggressive. And the buffer-based and Dash.js is pretty aggressive in terms of switching. That's one of the reasons why their overall QoE is bad. And robust MPC is more conservative because we are optimizing for the lower bound. Next, they looked at the total rebuffering time. And as we can see, here fast MPC is really suffering from a lot of rebuffering event. And robust MPC is because it's more conservative, less switching, the rebuffering is less compared to the other. Okay. So next, I was really interested in this paper comparing with maybe, for example, pensive that we've just read. So what is pensive? So pensive is basically replacing the ABR controller with a neural network. Not surprising. And in the paper, they show this figure, which is basically evaluating pensive on the same data set. And we have different QoE metrics, which don't matter much in our context. And what we're interested in is how pensive compared to the robust MPC, or MPC in general. And it seems that it performed pretty well in comparison. So what's interesting is that there is another experiment in the paper. So on the x-axis, we have different types of networks. On the y-axis, we have the average QoE again. And these results have been independently reproduced by a course at Stanford, CS244, if you know. And the two students reproduced their work and basically saying that there was no sound statistical evidence showing that it's significantly better, right? I mean, it's particular to their experiments, but this shows something. So I was really curious what's happening here. Now, as Carter has mentioned in his review, I also looked into Francis' paper, and on the x-axis we have the time span stalled, so stalled rebuffering. Okay. On the y-axis we have the average SSIM, which is basically a measurement metrics for the quality of the video. So the best methods are always to the left corner, right top right corner, and this axis is reversed. So here we have the pensive, and these are the MPC-based methods. So they are pretty close. And we have the buffer-based methods as well, and they perform surprisingly well. Right? So, and the Fugel is what proposed in the paper, basically a combination of ML and MPC. So instead of using a harmonic mean, we are using machine learning model to predict the throughput. And so what I wanted to say is that they are pretty comparable, and we shouldn't lose hope in traditional control methods, right? As we are having more fancier and fancier machine learning AI and ML methods. So just to quickly summarize what we have, so the strength, I think it's really interesting to see the theoretical control, the theoretical formulation of the problem space from first principles, and also as well as the QE objective that's being widely used this formulation nowadays. And it introduced the MPC into the problem space, and to nitpick a bit, we have some biases in the throughput prediction, which is in the author's term orthogonal to their work, and also I think Carter would have also mentioned, for example, the interaction within among multiple video players as well. Yeah, that's all I have, and I'd like to take any questions. Thank you.